Good afternoon. My name is George Paris. I am the CEO and principal owner of the company Directed Energy Materials. I think we were established in about, I think it was 2018. And we published a video last summer, that would be like September of 2024, which was an introduction. And we have been working along since then. And we've got quite a bit of new material. And what we're doing right here is we're providing you with a new video that summarizes both all the work we did up to 2024 and into 2025. So if you will give me a moment here, we'll see if we can make this work. Okay, as our name suggests, Directed Energy Materials, we were founded primarily to develop manufacturing technologies, especially additive manufacturing, but our portfolio now includes mechanical, electrical, and medical inventions. All right. Our business plan is to license our inventions and collaborate with our clients. We're also looking for investors who want to get involved with a startup company. We're a very tiny company at the moment and are flexible and interested in a lot of different possibilities. This is my contact information. Antimony_121@hotmail.com is my email address. I do most of my business that way. You can also call me on my phone, 301-602-1756. If you call me, make sure that you mention this video or the company very early in the conversation, because I get lots of spam type calls, and if you don't want to be treated rudely or hung up on, let me know that you're serious about talking about this company. Directed Energy Materials LLC introduction video 2024 is already on YouTube. It's available out there if you want to take a look at it, and that would update you through like September probably of 2024. We have this video is to supersede that, but that one does have useful information in it. Okay, at the moment, as of April 2025, we have 4 issued patents. We now actually have 5 issued patents. I'll talk about the 5th one a little later. The first patent has to do with using proton beams to cure resins. Interesting possibilities there. In conjunction with that and some other work we're doing with curing of resins with UV and some other things, we developed some other technologies having to do with the ability to visualize what you're doing in a pool of resin, and also how to separate a solid material that you're creating within a pool of resin from the liquid resin, the residual liquid resin. So I'll show you examples of that and how it works. Okay, I've always made the assumption people knew quite a bit about proton beams, but actually people don't. And so I'm putting some fair amount of technical discussion into these videos. If you know all about it, you'll find it boring. If you don't, hopefully you'll gain something out of it and be able to appreciate what we're doing. Now, in the lower left-hand corner, you'll notice a star that represents a proton flying through the medium, comes to a certain point, delivers a lot of energy, and that energy allows you to polymerize a resin to make a solid out of a liquid. Keeping that in mind, let's talk about the comparison of proton beams, something you don't typically encounter, with something that's more familiar to you, how photons work. Photons are electromagnetic radiation, and we're talking about visible light, we're talking about X-rays, we're talking about ultraviolet light. And if you were to take a flashlight and shine it into a pool of water, you would expect that most of the energy of the flashlight is going to be on the surface, and that after that it's going to taper off. And that's exactly what is happening. Most of the energy density, the highest energy density, is at the surface when you use photons, and then it tails off as the photons are absorbed as they go into the medium. Now, if you have a target that's buried some distance within the medium, this is not necessarily the ideal situation. Most photonic interactions are used to address things which are definitely on or at the surface of the medium. But if you've got something buried inside the medium, you have a whole new problem. And so the counterintuitive phenomena of proton beams is that the proton beam travels into the medium and at a certain point delivers a high dose of energy. Now, the way that works, a proton is a very, very tiny positively charged particle. From the viewpoint of a proton, any mass, any material looks like a negatively charged field because you have all these atoms that have positively charged nucleus, but the vast majority of space in any material is occupied by the electrons. And those electrons are all negatively charged, and when you send this positive charge through there, we talked about at high speed, high energy, we're talking about millions of electron volts of energy. So these are things that are moving very, very quickly. As they go through this negatively charged field, they are being slowed down. There's an electromagnetic drag on them. And as they slow down, the amount of energy per increment of depth that is delivered goes up because they're getting slower, and so they're spending more time and delivering more energy to a short distance. Actually, this relationship is more or less related to, it's called the linear energy transfer. This is the kinetic energy of the particle that's transferred to the medium, and that energy transferred to the medium per unit of distance within the medium is related to 1 over the velocity squared. So as the particle slows down, the velocity approaches 0, velocity squared approaches 0, and 1 divided by 0 is a very large number. And so what happens is the amount of energy that's delivered at what we call the Bragg peak is very high, and it's uniquely deep within the material of interest. So this is a unconventional, counterintuitive type of phenomenon. And like I said, most people don't get much about it. Now, one of the things you'll notice is that after the proton stops, it no longer penetrates into the medium, and there's no energy delivered beyond that point. Now, if you went back and looked at the video or the slide I had earlier, the X-rays, etc., just keep going. So there's a difference there that's very important because you can control the depth at which anything happens very carefully. And you can define this proton beam, the so-called Bragg peak. By the way, the Bragg peak is named after a father-son team of the Braggs who were working, they were physicists working back in the 1920s, 1930s time frame. And they're the ones who first observed this phenomenon. So anyway, keep in mind, I'll use the term Bragg peak, and I'll talk about linear energy transfer, and understand that proton beams, the energy delivered to the medium, that is the energy density delivered to the medium, radiation dose, if you want to talk in that terms, is going to be related to 1 over the velocity squared, and as the velocity goes off to 0, the amount of energy delivered skyrockets. So anyway, let's go to the next slide, and I'll show you an example of this. What our patent, this was actually from December of 2022, entails, these are drawings from that patent application. If you had a medium that is basically and we're using liquid resins, that would be number 1 in this scheme, and you fired a proton beam, that would be number 2 in this scheme, into that medium. That proton would slow down and at some point would come to the point where you're approaching 0 velocity. The linear energy transfer would skyrocket as indicated in the graphic above. And at that point, you have the highest probability of having a basically you're trying to, if you want to take a liquid resin and turn to a solid resin, what you're doing is you're uh, having a free radical or electronic ionic chain reaction occurring. And so you need a certain amount of energy density to get that chain reaction going. And if you manipulate your doses correctly, you can have a situation where nothing much happens until you get to the near the Bragg peak. And so the number 3 in this screen here is representative of forming a solid within this liquid at the Bragg peak. And by setting the total dose number, that would be 6, that little horizontal line across the graph. If you set the total dose at a place where only the Bragg peak density of energy will cause the essentially catalytic reaction among the monomers that are turning into the polymers, then you can create things, cause things to happen within the liquid resin. So I'm going to show you a beautiful example. This is one of the first things we did. We thought that you have to appreciate proton beams are not something you go get off the shelf. It requires some very expensive hardware to do that. And the only people who have them routinely are people who are doing primarily oncolytic, that is to say, breaking down tumors. They're oncologists who are treating cancer. And so we tend to find ourselves working with oncologists and physicists who work with oncologists. And all of our actual work has been done in cooperation with the Maryland Proton Treatment Center. They're up in Baltimore. And there's some very nice guys up there these are physicists who are interested in dosimetry and quality assurance, and they want to make phantoms. A phantom is a physical representation of some sort of a medical treatment. So anyway, we wanted to see if we could make a representation of what the proton beam does in a medical environment, a medical application. So we took a plastic skull. This is a anatomically correct plastic skull, and we outfitted it with a spherical plastic container, and inside that plastic container we created a 3-dimensional index array, some little balsa wood sticks that are in there in the right positions to indicate, left, right, up, down, back, front. And there's a resin, liquid resin is put into the same sphere, and then the whole thing is set in the skull and put in a position to be hit by a proton beam. That's the example to the right. That'll be just above my head it'll be just to the left of my head in your screen. Now, unfortunately, in spite of my best efforts, this cameo of me talking is actually obscuring the picture of the skull and the hardware that's used to provide the proton beam. That red line that you see coming down would be representative of the proton beam that has been targeted at the skull. And lo and behold, if you look at the center bottom photograph, what we have done here is the liquid resin has solidified, turned blue. I'll explain the color change later. And all of the unreacted liquid resin can be drained out of this container. It's actually dripping across my little finger there. So we have successfully demonstrated several things here. One, we actually hit the right place with the proton beam. That's important to know, that the proton beam is in fact well controlled and people know exactly where it's going. We hit it right at the intersection of our indices. And you'll notice that the only resin that was solidified was at the Bragg peak, and the other resin, which is not this very light blue color, was not affected at all. It's still liquid. It's draining out through that hole at the bottom. And so this is actually a physical representation of what happens when you get proton therapy. And I'm surprised that most people apparently trust their doctors, because most doctors will show patients a graph of the linear energy transfer, which we showed you earlier, and they'll give you some cartoons that look something like this, and they'll say, hey, we're going to shoot this proton into your skull. It's going to go through your skull or through your body. It's going to go to the tumor, which we have located accurately through various scanning techniques, and it's going to do damage to the tumor, but it's not going to hurt anything in between. Now, that's a counterintuitive idea, and I'm a little surprised that people are willing to acquiesce to that. But I guess doctors and surgeons and whatnot are used to the problem of trying to convince patients to do things that sound a little unusual to the patient. So, and apparently the patients, or I wouldn't call them gullible, but they are trusting. So anyway, but this is a actual physical representation of that process, and it's the only one I'm aware of. I've never seen anybody who could show this off to a customer or a potential customer, a client, a patient. And we have shared these diagrams, these photographs with various physicians that are in this business, and I hope that they are taking some of these pictures of this that we gave them, and they're showing their patients, and the patient hopefully will feel more confident that, hey, this guy is going to send a proton into my body. It's going to go through and not cause any problem until it gets to the tumor or whatever it is I'm trying to hit, and it will then deliver its energy and cause the damage to the tissue that we want to kill. So anyway, that's one of the first things we did. It's, I think, an important dramatic demonstration, and it's the only one of this type I'm familiar with. Now remember, we really wanted to do manufacturing. We weren't, the medical part of that was fun and games, but it was not what we were actually trying to develop. It's not what our patent was actually targeted at. So we have done some, we've taken some time from the proton beam people, and we have done some experiments with manufacturing type processes. And this is an interesting one. On the left-hand side at the top, what you see is a plastic box, and in that plastic box we have mounted a metal frame. Actually, it's two pieces, and between those two pieces we have compressed a stack of aluminum screens. These are very fine screens, so you can't see the holes looking at them at this, under these conditions, but they're tiny little holes in these aluminum screens. And what we did, we put the screen between the two plates, held it all rigidly in place, and then we filled the box with resin, and then we pulled a vacuum on the box so that the air bubbles that are trapped in the aluminum screens would come out and the resin would go back in. And then we took that box, and we were trying to, we decided that the easiest way for us to control this slowing down process that I've been talking about was actually to bury that box under about 4 inches or 5 inches of water. So imagine we've got 4 inches of water above this box, and then you have the box, you have the screens, you have the resin, all that stuff in the box. And we calculated how much energy we need to go into the protons to get them to hit the Bragg peak at the screen. Okay, that was a calculation done by our physicist friends. And lo and behold, we shot two shots of the proton beam through this contraption, through the water, through the resin, through the aluminum screen, etc. And what you see on the left and in the center, the lower left and in the center, are pictures of that, what happened, the solidification of the resin. And I think these are the back and the front of the same stack. And what you've got there is this was after, of course, we took it out of the liquid resin, washed off all the liquid resin with organic solvents and whatnot. And this is what was left over. The solid resin was penetrating through the aluminum screens, and essentially were like a couple of nails that went through there. And I think this implies that there is a manufacturing application, considering especially that we worked through several inches of water, went through the plastic, went through the resin, and produced these penetrating solid resins in the right places. Now, at the top, what you see is a profile of this whole thing. So you see the depth of the proton beam induced solidification of the resin, and so these four photographs together give you a very interesting insight into the type of thing we could do with this. Now, the one that's just over my head, just to the left of my head, is a different animal. This is a different experiment. What we did here, we wanted to demonstrate several possibilities all in one experiment. What you have here is two pieces of aluminum honeycomb that looks a little hexagonal design in aluminum. Aluminum honeycomb is, of course, used in many places where you need something that has certain rigidity but not a lot of weight. And we put that in a container, and we fill the container, flooding the honeycomb with a slurry of aluminum magnesium alloy slurried into the resin. And so the whole thing was filled up with this resin, and then we exposed it to a proton beam while it was rotating. And that's how we managed to make something that looks like a donut. And once we had done that, we took the whole system apart and used solvent to wash the excess, the unconsolidated resin, the liquid resin, was washed away. And when that happened, you had what you see here. This is actually the aluminum magnesium powder, which has now been consolidated and embedded in a resin base, and the resin is holding everything together, and the donut in the middle is between these two pieces of aluminum honeycomb. So it's just a toy we created to demonstrate several possibilities here, and this is very close to the technology that is used by some manufacturers to produce metal parts from various types of 3D printing. So we did not go to the process of trying to take the resin out of it, and what they would typically do if they, with other systems, is they wash away the resin, and then they take the part and they sinter it. That is to say, they melt it in place so that now you have a solid metal part that is all consolidated, not just the particles of the metal that are all scattered amongst the resin, which is acting as a glue holding them all together. But obviously we're in the direction of making a metal part there. Now, as I was talking, we encountered two problems in working with this. One is that if you just take a liquid resin and you shoot a proton beam in it, you're likely not to be able to tell if anything happened, because it turns out that the solid resins have refractive indices that are very close to the refractive index of the liquid resin. And so they just sort of disappear in there. It's like you can't see it. And so we have this problem of visibility, that, like, have we done anything or not? And that's sort of demonstrated at the top here. You'll notice the top layer here is the liquid resin, which has a density of about 1.05. That's Either you look at specific gravity or you look at grams per mil. And there's actually a piece of solid sticking up into it. You can barely see that there's something there, but it's, you really can't tell much about it because the refractive index of the solid and the refractive index of the liquid resin are basically identical. Now down below, what we have is a dense solution of literally sodium chloride in water. It's, that water and especially the sodium chloride solution is immiscible with the liquid resin. And so you get the two phases, and the aqueous solution is primed to have a density between, it's actually a gradient at the bottom where you have actually some solid sodium chloride. You have a density of about 1.2, and then up towards the top it's about 1.1. And lo and behold, the suspended solids have a density of about 1.4, and so they sink out of the liquid resin and end up in the aqueous density gradient. And it accomplishes two things here. One, not only have you separated this material, but you've separated it without creating gravitational forces, and you have not created viscosity forces. If you create a material in the middle of a pool of liquid resin, and then you try to take that solid material out, what you find is that if it's a very, not a massive type of material, if it's got some very fine structure, if you try to pull it out, the viscosity of the liquid resin is going to cause viscosity drag, which is going to cause the bending and deformation of whatever it is you're trying to manufacture. That's a problem. But then you'll notice there's no supports, and so there's a gravitational, if you get this thing out of a gravitational field, if you got it out of the resin and set it on a table, it would just, probably crumple down, because until the resin gets a chance to fully solidify, it's still flexible and still gets moved and bent. And so what we've done here, we've eliminated both of those problems. First off, the sinking process tends to be slow and progressive, and so that allows you to avoid viscosity drag, which would cause deformation of your material. And then you also, because you're sinking into a density gradient, you essentially avoid any substantial gravitational deformation of the object that you have created. So this is I think a very nice way to do the separation. And if you're trying to do something manufacturing wise, you're faced with that problem of how to avoid those deformations. And I think this is one of the best ways to do that. Now, the other problem we've talked about is visualizing the thing we're trying to make. And so the way we've solved this, and this is the other patent that we have done there, is we have discovered that you can take what we call leuco dyes, and the one that we're working with primarily is leuco crystal violet. Leuco means colorless, and so there's a form of crystal violet that is colorless, and you mix that in with the resin, and you don't notice that it's there. You might, if the resin has reacted some and started forming solid, you do start seeing blue color, but it's typically very light, because what you're doing there is you're actually monitoring the degradation of your resin. I can see an application where a manufacturer of a resin would want to put the leuco dye into their products to prove to their customers that, oh, by the way, this is a good batch of resin because it hasn't turned blue. When it turns blue, throw it away because it's past its prime. It's been heated up unnecessarily or something, exposed to UV light or something that is basically turns your nice resin into a partially solidified mess. In any event, what you see here are three examples of things that we have produced, either by proton beams or with laser beams, in which we were able to identify the fact that we actually have had reaction, and that reaction is demonstrated by the intensity of the color. So if you get a very small amount of reaction, you get a very small amount of color. If you have a very serious, extensive reaction, then you have a lot more color. So let's go to the next slide, and we'll see a better example of this. Let me try to center myself in the cameo box over here. On the left extreme side, at the top you see a picture of the setup we use. This, you have two lasers, one at the top. You see the little blue dots. The one at the top is the vertical laser, and the one on the left is the horizontal laser. And those two lasers were coordinated such that they intersected within a pool of liquid resin. And this whole process went a few seconds. It was much less than a minute, just literally probably 10 seconds or less. And in the process, we noticed, and this was very useful to us, we noticed in the lower left-hand picture, you'll notice that there's something a little light blue, looks like a little donut, sort of floating in space there. Well, if we hadn't had that dye, we never would have seen that. We would not have realized that, hey, we have done what we wanted to do. We caused a chemical reaction, solidification of the resin in a very specific location. It is not on the bottom, it's not on the top, it's not touching the edge, there's nothing in the middle. It's just this donut shape that we created that has turned blue. And this allowed us to just go in with a probe, which we did in the center, and put the probe through the center of that donut, pull it out, and you see it draining off here. The liquid resin is draining off the solid. And then once we have cleaned this up, rinsed off the excess liquid resin with solvent and allowed it to solidify. This is actually an acrylic resin, and sunlight immediately solidifies this stuff. The liquid resins or acrylic resins get pretty hot. They're actually, the polymerization process is pretty exothermic. And so what you see, which was actually partially obscured by me in this cameo slot, is the part, you'll notice it's hard, it's clean, it's dry, and it's rigid, and that we were able to do that literally in a few seconds. This did not take long to do, and we did it with the two lasers that were overlapping, and maximize the energy density within the resin. That was the process that we were using. This is I could show you, these are sort of an overkill here. This is where the two lasers came together. We pulled the solid out, we dried it off, and that's it. But anyway, the point here is really that without the dye in the resin, we would have never figured out what was going on until it was too late. Because eventually you'll get a solid, but it may not be the solid you're looking for. So the dye allows you to very fine tune the amount of energy that you're putting into your system, because it tells you exactly where and how much solidification you have achieved. Now we're going to go to something entirely different. Let's see if I'm here. I still have problems getting myself out of this lower right-hand corner, and I'm partially obscuring this. One of the first things I got interested in was graphene, carbon nanotubes, and these highly conductive, very strong materials. And everybody talks about how strong they are and how much electricity they conduct, and you get these beautiful drawings like the ones on the left. And then if you ordered this stuff, if you can go on Amazon and order a bunch of carbon nanotubes, and what you get in the mail looks like this pile of black stuff on the right, which doesn't look like much of anything you'd want, and doesn't have any particular strength or electrical conductivity advantages. But it is, because it is a very finely divided material, and it's randomly oriented in this finely divided state. And so we wanted to be able to create, nice oriented uh, patterns of essentially carbon. And we were, we of course we'd love it to be carbon nanotubes or something like that, but we're satisfied just by having electrically conducting carbon, and that's pretty easy to occur. Unless you have a diamond, you have electrically conducting carbon, and that's what we are going for here. And we're doing this by a different pathway. Now, your your physicists dominate this whole thing. If you look up manufacturing carbon nanotubes or graphene, you're going to find some physicist who has got some system, for example, chemical vapor deposition, in which a fairly stable molecule such as methane is being blasted with an enormous amount of energy, breaking it into pieces, and you've got just these carbon atoms that are finding one another along the way. And you have no real control over what's going on. It's all driven by uh, concentration, kinetics, and thermodynamics. And so it's really a just blasted with energy, and let's hope something happens. Now, I'm a chemist, and that's not the way I think. Chemists don't think about taking methane and trying to make graphite. Uh, Chemists say, hey, let's start with a chemical compound, a carbon compound, that will allow us to control the reaction to go in the direction we want it to go. And so we did a little literature searching and came up with the following. It turns out that, and this is patented, this is a patented process and idea. Um, the Back a while, Dow Chemical Company was making a variety of polymers, polyethylene type polymers. And if you take 1,1-dichloroethene or 1,1-dichloroethylene, if you prefer, if you happen to be a chemical engineer, if you had a bottle of that stuff sitting around on the shelf for a few weeks, you would go and open it and you'd find out it was all solidified because it polymerizes very nicely at ambient temperature to give you a linear polymer that is analogous to um, polyethylene, except that every other carbon has two chlorine atoms on it. All right, and so it's really a dichloropolyiethylene product. Now, it turns out, and this is the part that intrigues us, is that you don't have to heat these things to thousands of degrees to get rid of the HCl. If you heat it to, say, 200 degrees, this polymer, the dichloropolyiethylene polymer, breaks down, splits out a mole of hydrochloric acid. For every monomer that went in there, you get an HCl out, and you end up with a linear polymer, which is a chloroethylene uh, material. And when we realized that, we said, hey, we're almost home free here. We're going to make carbon nanotubes and graphene left and right. That's not quite the way it worked out. It turns out that if you heat this stuff up to around 700 degrees, you do split out another mole of hydrochloric acid, but it turns out that there are other reactions that are going on in there, and they're probably Diels-Alder 2+4 cycloaddition reactions, which gives you cross-linking, which you want, but it gives you random cross-linking that is not concerted with the appropriate loss of hydrochloric acid. And so you actually get a randomized cross-linking mess, which does conduct electricity, but it is not it's certainly not carbon nanotubes or graphene. But we're not really expecting to have perfect material because we're just going to try to make some electrical components out of it. Now it turns out if you want to take this material and heat it up like 2,000 degrees, which is like the type of temperature that the physicists like to work in, it's also a temperature that is used to make carbon fiber. Carbon fiber is made from polyacrylonitrile, but carbon fiber has to go through a couple of steps an oxidation step and other types of steps, which make it kind of messy. But this stuff, you end up with a very pure carbon. Once the hydrochloric acid is out, you got very pure carbon. But if you heat that up, then you can make something that looks like a carbon fiber out of it. But that has to go up to like 2,000, 3,000 degrees. Now, what we're trying to do is we think there's some fairly simple ways to try to control this second step where we say 700 degrees C. We think we can mitigate the premature or uncontrolled cross-linking amongst these chains. And hopefully we can figure out a way to either make graphene or carbon nanotubes in a fairly straightforward way. And that is sort of one of our research goals. And we go forward from there. But this is a patented process. We're actually using a laser to take the monomer to a carbon form. And so our patent, this is a diagram from our patent. We have a inert substrate that sustains high temperature. The monomer is absorbed onto the substrate, and then heating the substrate causes the monomer to polymerize and to decompose, leaving behind a trail of carbon. And so this gives us a way to like write the carbon pattern onto the substrate. And we're not entirely sure what the composition of that carbon is, but we are quite sure that you make carbon this way and you can get rid of all the HCl. And of course, after you deposit the carbon, you can wash away any excess monomer or the polymer that might be around there. So we think this would be a way to you could use this to draw out electrical circuits or various types of connections between different electrical components. And we also are looking. We have an issued patent in here, but they didn't approve all of our claims. We have some claims that we're still arguing with the Patent and Trademark Office with, and we hope the examiner will eventually come to see our points of view and allow us some additional claims. And when that happens, we have ways to modify this solid that we're depositing to hopefully get other types of electrical properties. We think we can make semiconductors. We think we might be able to make transistors. We think there's a variety of things we could do here. But this is all within our patent to use this technology to lay down patterns of carbon on a inert substrate. Okay, so that's all sort of old news. The question is, what have we done for you lately? And what's new in 2025 is a good way to state that. Now, to introduce this, let me remind you that we have ongoing research and development in mechanical, electrical, and medical fields. And because of my prior history, I've dabbled in some medical fields as a chemist, and we fraternized with physicians and medical people. And we have also got this ongoing relationship with the Proton Therapy Center. So we think about medical issues quite a bit. Now, the first thing I'm going to talk to you about, however, has nothing to do with anything that we've talked about so far. It's an entirely different technology with an entirely different type of product. And we would love to have somebody come by and say, hey, we'd like to incorporate that into our business plan. Here is what we're doing, looking at the various applications that are out there. We think that we have some new and different things to do. Okay, the patent is going to be issued on July 1st. I'm talking to you late in June of 2025, so this is a couple of days in the future, but we have already received notice about what the patent number will be and the name and stuff like that. I don't know what the patent name is. It's probably a very Baroque sort of name, but we call this internally, we call it enhanced brachytherapy. Okay. And in order to explain to you what enhanced brachytherapy is, I need to go back and explain what brachytherapy is, because that's probably not a topic that most of you are familiar with. If you are familiar with it, please call me and ask to license our technology, because you think you could probably use it. In any event, conventional brachytherapy involves implanting radioactive seeds into a tumor and letting the radioactivity kill the tumor. Now, the seeds themselves typically have a iodine isotope with a few weeks half-life, and most of the energy is actually retained within a titanium capsule, which is biocompatible. But this thing works because escaping from the titanium capsule, you have gamma rays and X-rays. Now, they're not very powerful gamma rays and X-rays, but they do penetrate a ways into tissue, and they kill indiscriminately. There's no discrimination between a healthy cell and a cancer cell. Okay, so it's a completely indiscriminate killing process, and has to be sort of carried out that way. It's basically a way of selectively killing a bunch of cells. Not selectively, but just selectively only in the sense of where you put the seed is where you kill the cells. Okay. Now, we want to do it selectively. Part of our, directed energy concepts, basically we're thinking in terms of controlling these types of behaviors to the betterment of mankind. And we would like to be more selective in our killing process. And we'd also like specifically to do something about metastasis. Now, if you talk to oncologists, it turns out that metastasis is really the thing you don't want to hear about. If you've got a localized tumor, it can be treated, it can be removed surgically, typically, things like that. But once this tumor starts going through a metastasis process, you have new tumors popping up all over the body. And there's a lot of debate about what causes cancer, how it reacts, and what causes metastasis and all that. I have my own personal opinions about what is important in this, and that is reflected in this patent that has been proposed here. I believe there's quite adequate literature, scientific support for this, not necessarily from me, from other people who have studied the same thing and come to many of the same conclusions. Going to that step, I'd like to point to a gentleman named John Poelick. John, I was not a great friend of him, but I certainly knew him and respected him. He's a great humanitarian, civil rights advocate, all that sort of thing. Had some very interesting history there. I think he's at Yale. He recently died, unfortunately, and he left behind a whole series of very important papers. And the thing that made it most important is that he was following this of a particular pattern. Now, one of the things that I was interested in this area was cell-cell fusion. It turns out that your cells undergo fusion, and then you get what's called a hybrid cell. And sometimes, this happens accidentally, this happens on purpose, there's various ways it happens. But it turns out that the issue that John was interested in, and which I also was interested in, and some of my colleagues were interested in, was the fact that leukocytes, which are leuko means white or colorless, these are the white blood cells that run around your bloodstream. Leukocytes do tend to fuse with a variety of cells, and in particularly they will fuse with tumor cells. And John is the person who, he and his research group, demonstrated that leukocytes fuse with tumor cells, that's called hybridization, and they can initiate cancer metastasis. That is a formal explanation, a formal demonstration, which many of the other of us who've done work in the area and speculated in the area have not actually demonstrated that, this is a gateway to metastasis. Now, that was his 2020 paper. In 2021, another paper came out of that research group. It says a melanoma patient with macrophage cancer cell hybrids. In other words, you have a fusion between a macrophage, which is a leukocyte, and a cancer cell to provide a hybrid. And in the primary tumor, they found these in the primary tumor. They found them in the lymph nodes associated with that primary tumor, and they found them in metastases that were in the brain. So he actually traced out the pattern of metastasis. He went from the primary tumor to a lymph node and ended up in the brain, and they showed that they had these very unique hybrid cells had made it through this whole process. Now, my opinion is that most of your danger of metastasis is probably related to this process. It goes back. I can give you some of the lines of argument. I will in a second. But here's another paper. This was 2024. Maricot, et cetera, and colleagues. They have done something similar. They have phenotypic characterization of dual nature. That when they say dual nature, they're talking about hybrids between macrophages and cancer cells from uveal melanoma. And so they're working in the same area and starting to demonstrate some of the same things that the John's research group was demonstrating. The point I'm making here, let's go back a little bit. What's going on with leukocytes? What are these immune cells? Well, how does your immune system work? Basically, the immune cells are created in the bones, and they wander away from the bones and are transported just randomly in the bloodstream. And they are held. The reason they don't just all flood off at once is because the bone releases what's known as a chemokine or cytokine, which basically is an attractant that causes these leukocytes to be attracted. Now, leukocytes are motile. They move on their own. They don't just go with the flow. They can just go with the flow, but they can also move and do very specific things that other cells do not do. That's how they work as part of the immune system. So you got these leukocytes floating around in your bloodstream, and suppose you have you cut your finger and you get an infection, and there's this infective process going on, and what happens is that infection releases chemokines which attract leukocytes. And so here's a leukocyte floating around in the bloodstream, and it happens to say, oh, here I have, at this particular point in the bloodstream, there is a large source of this chemokine, and that tells me, A, to stop, which is not trivial, bind myself to the wall of the blood vessel, penetrate through the blood vessel, which is not something that a normal cell would do. Your platelets and red blood cells, all that stuff, don't disappear out of the bloodstream randomly. They're contained in the blood vessels. But the leukocytes can pop out, go off, migrate into the tissue, find the point of infection, and start killing off the infective agents. Or if you have a tumor, it also causes this chemokine signal to be sent out. It's like the bat signal. Here comes Batman, stops at the right place, gets out, and goes and climbs through the cells into the tumor and starts killing off the tumor cells. Well, unfortunately, the leukocytes also fuse with the tumor cells, as the publications that I just indicated before. And the sad thing about that is now you have a cell. It's a hybrid. It's got the bad properties of a cancer cell. In other words, it's out of control. Its cell cycle is not regulated. It's reproducing itself rapidly, and then it also has the properties of a leukocyte, which means that it can go move out of the tumor into the bloodstream, move around the bloodstream, and it's going to be attracted to locations where there's high concentrations of these chemokines, which includes the bones and some other places, probably the lungs and some other places within the body. So you get these metastases. You have a tumor in your big toe, and the next thing you know, you've got a metastasis to a bone. Or more likely, a more realistic example, suppose you have a prostate tumor. You've got a tumor in a prostate gland, which could be contained and gotten rid of fairly readily. But the next thing you know, you've got a tumor that is a metastasis in a bone because something got out of that uh, uh, prostate gland, and now it's gone and found a bone because it was drawn to the bone because the bones are excreting these chemokines that draw these leukocytes in, and this leukocyte that is hooked up with a cancer cell is now attached to your bone and is now causing a tumor to grow in your bone, which is not a pleasant thing to think about. So, keeping all this biology in mind, my question was, how do we take that knowledge and how do we turn it against these these renegade hybrid cells that are likely to cause metastasis? So on the paper that I wrote back in 2015, it's published in one of these Springer documents. It's called Cell Fusion, Chemotaxis, and Metastasis. It's in a document that was edited by Dr. Candos, and the title of the whole uh, group of papers is Intercellular Communications in Cancer, and that was just my one contribution to his overall book. And basically here I have a little diagram on the left. By the way, my abstract to my paper is in this box on the right, directly above my head and partially obscured by me. In any event, over here on the left we have a motile cell, which is typically a leukocyte. There are some stem cells that also fall into this process, and you have a cancer cell, and they fuse together, and the product of that is this motile cancer cell, which is subject to metastasis. Okay, so I've got a chemokine source, and it's broadcasting out chemokines. It attracts these hybrid cells that are motile cancer cells. And how can I use this to defeat the metastasis process? And I could read you this slide, but you could read it on your own. And what we have designed and what we have patented is a system for doing that. Rather than having a fully encapsulated bead which sends its radiation out into the vicinity, what we're proposing to do is have a bead that has a hollow part inside. This could, the actual conformation of this could be any sort of an envelope. It has to be a biocompatible envelope, and we're going to not put a radioisotope that creates gamma rays in here. We're going to put isotopes that only produce either alpha or beta particles. Now, if you know your physics, you know that alpha particles and beta particles do not penetrate outside. They're very easily contained, and they move in straight lines. And so what we're going to do here is we're going to put, if you look at the number 412, this is either going to be an alpha source or beta source or both, and it's positioned such that the radiation particles that are flying away from that source move in straight lines and cannot reach the outside of the device. In other words, these seeds would not have gamma rays or any radiation coming out of them. They would be designed so that the radiation was totally enclosed within the device. Now, the second part of the device that's important is the chemokine, which is the 410 item there. And the way this is going to work, the chemokine is going to diffuse out of the device, out of the envelope through an opening, and it's going to be detected by motile cells. That this might be a normal leukocyte, or it might be a cancer cell. And here we come. That's attracted into the kill zone, and within the kill zone, you have this radiation which blasts it, and alpha particles are going to make short work of these cells that make it in there. And once they're killed, they break up, and you can have other cells and actively find their way in here. So this is random cells are not going to tend to come in here. It's going to the cells that go into this kill zone are actually going to be motile cells and cells that are attracted to the chemokine, and you can use the chemokine to select which leukocytes you're going after. Different leukocytes are attracted to different chemokines. There's a whole families of these things, and by selecting the correct chemokine, you can select a particular leukocyte or a particular motile cell. And so this is the subject of our patent. The patent has been issued, and we would be very happy to have someone call us up and say, hey, we would like to develop this into a product. And we would say, great, let's work out some terms and conditions that would be beneficial to you and to us. And so that one is on the board. We are really not in a position to do a lot of development in this area. It includes a lot of micro engineering. You've got to make these seeds that we're talking about here are envisioned to be on the scale of the same as a seed. With those seeds that I was talking about earlier typically are about 0.5 millimeter in diameter and about 5 millimeters long. That's like 5 millimeters is like 0.5 centimeter. So the diameter of this particle I'm looking at here is probably on the order of 1 millimeter or maybe 2 millimeters, something like that. So these are not big things. So this is not something I'm going to do in my garage. But a company that's got some skills in manufacturing things like this and has some knowledge of it can put something like this together, and we would be very happy to work with somebody like that. Now, while we're doing all this research, we've looked at chem abstracts, we've looked at PubMed, we've looked at patent abstracts, especially about the proton beam, because we've been working with it for the longest. And one of the things that surprised us is what we did not find. We had an idea, and we said somebody must have done that. And we looked and we looked and we looked, and we can't find any reference to anybody having the idea that we did. And so we did some experiments with our colleagues at the Maryland Proton Treatment Center, and they are co-inventors on the patent that we have submitted. Basically, we said, okay, we're not microbiologists, but we can get our hands on some petri dishes, and we need to design a system where we can send a proton beam into a petri dish. And so the first thing that we did, we took about 10 petri dishes, and we in a stepwise position here, we got our hands on some fecal bacteria, a broth of fecal bacteria, and we inoculated these individual petri dishes. All of them were inoculated with the same stuff at the same time, within minutes of one another. And then they were stacked up, as you see here, and probably about 18 hours later or less, they were irradiated. Now, this was our first experiment, and we said, well, we were kind of sloppy. We weren't collecting all the data we probably should have. You'll notice on this red cap at the top, these are numbers. The numbers are 0, 2, 4, 8, 16, and 32. And what that represents was a number of seconds that we were going to expose the petri dishes to these proton beams. We had a particular proton beam energy and whatnot in mind, dose rate, etc. And so we did that experiment. We took, within 18 hours of inoculation, we took the whole system over and exposed it to proton beams for the allotted amount of time. We took the samples back home, disassembled this whole thing, and let it essentially incubate for a couple of days. And then we took a look at what we had. And if you look here, number one was the top item, one at the top, which received the least linear energy transfer. And you'll notice that there's a pretty healthy growth of different bacteria over here. And you'll notice that it's not symmetrical because the doses, someplace there's a 0 and someplace there's a 32, which are unfortunately side by side. And then you had out in the middle, you had doses for like anywhere from 2, 4, 8, 16. And so that's probably more the center part here. Anyway, you have some asymmetry in this population. And we see the same thing in 3. What you see fewer colonies, and you see a similar asymmetry of the colonies. If you go down to 6, you have more asymmetry, or have the same asymmetry, and you have fewer colonies. And if you go down to 8, there's almost no colonies at all. And 8 is about where we would expect to see the Bragg peak for all of these. This is the estimated position of the Bragg peak. Bam. And guess what? We are seeing something, the radiation is killing off the bacteria before they can multiply. And as soon as we realized that, we filed a provisional patent that's been out for over a year. And we decided we'd do some more tests, some more experiments. And we wanted a system where we could send our proton beam down through some agar and sort of see. We wanted to grow the various organisms on the surface of the agar, between the agar and the air. And so we wanted the proton beam to go just below the surface down the length of this. And so we have invented a tube. We basically take a plastic tube about 10 centimeters, 12 centimeters long, and fill it 2/3 of the way full of liquid agar. Then we lay it on its side and let it cool in a refrigerator, and we end up with a very nice cross section, very much like the circle on the left here. And then when we fire our proton beam down through here, it goes a certain distance, as showed by the graphic here. The graph shows where the linear energy transfer is and where the Bragg peak occurs. Bam. And we would expect that from all the arguments I've told you, we would expect a progressively more effective anti-microbe effect along this as we turn to the Bragg peak. And then at the Bragg peak, we would expect a pretty dramatic effect. And then, interestingly, beyond the Bragg peak, we wouldn't expect to have any effect. And so we did this, and boom, here's what we got. Now, take note, when we did the experiment, we actually inverted these tubes. We were just like, this is like our first experiment. And so we inverted this tube, lined it up properly, and the proton beam came in from above. The metal cap is at the bottom, and based on what our calculations, based on the density of the auger and all that sort of thing, we assume that the Bragg peak would be somewhere about where the tube enters into this tray that we created. Now, when we took it out and started looking at it, we inverted the tube such that the cap is at the top now. And lo and behold, if you compare the control, we only had one control and one test here. The controls had pretty much uniform growth and fairly thick growth of whatever this is. We think it's a fungus. It's probably I can't think of the name off the top of my head, but this is actually the inoculation here was with a broth of microorganisms abstracted from soil. It's actually sold. You can buy it on Amazon. It was used to. They say it improves the quality of the soil. We didn't care. We just wanted to see if we could grow something out of it, and sure enough, we did. And you'll notice that where the Bragg peak was expected, there's a blank spot in this tube. And beyond that, lo and behold, there's still a fair density of material, fair density of growth. Now, if you compare the area before the Bragg peak, you'll notice that in the irradiated sample, there is some thinning out of that compared to the unirradiated sample. And so this is actually very much exactly what you would expect to happen when the proton beam is causing death of the soil fungus or whatever this is that is growing on this auger. Like I say, we're not microbiologists, and we are looking to expand our work with more precise methods and techniques from microbiologists. Now, that sort of summarizes what we're doing. Obviously, we think that what I just talked about there is potentially very valuable. We've patented it. We expect, we hope we have some favorable results from our patent examiners, but we don't expect to have any conclusive information for. We'll be talking about this in 2026 and maybe in 2027. But we are very good at arguing these cases, and we hope to be successful. And in the meantime, we are considering applying for some grant money to try to pursue this because we think it's pretty important. Okay, what about our philosophy and approach? This whole video is about the company, not about any particular product or any particular patent. Our approach includes, we are not cowboys, we are scientists. We do controlled experiments. We gather data. We collect the data. We tabulate the data. We analyze the data. And we have all of our notebooks and our reports, and we call them technical reports internally, and every major experiment we do has a technical report or two or three. And so we are involved with doing real scientific research. And we think outside the box. I think it's pretty obvious from what we've been talking about, the variety of different things that we've talked about here, that we have a lot of ideas. We are just scratching the surface. We have had some success in getting patents on some of those ideas. We're looking for other ideas. Every day there are new ideas, and it's a matter of how fast can we get intellectual property rights and how fast can we actually do demonstration projects. And so here's some, the type of scope of the types of crazy things that we've done. And we have lots of interesting stuff is ongoing, and we get our hands dirty. We don't shirk at trying things and putting our hands in resin and with gloves on and all that kind of stuff. We work with lasers and we work with electrical systems and electrical circuits and etching machines and all kinds of stuff. And we're trying a variety of possibilities. And like I said, we just have ideas which apparently nobody else ever had. At least they never tried to patent it, and there's no processes. And so we are a very innovative small company with with demonstrable success. And the important thing that you should remember if you're thinking about investing in this company or if you're thinking about using some of our technology is that we're just getting started. This is a very small operation. If we had more money and more people and more time and more space and more labs and all that sort of stuff, we would be doing a lot more exciting stuff, pursuing a lot of different projects. And what you see here are a few examples of things that we've done in our lab. And it seems that we've been drawn more into the medical field than the manufacturing field. Uh, we are equally interested in both. We think they all have major success and possibilities, and we would love to have someone join us in this quest. Again, my name is George Paris, Parris. My phone number is 301-602-1756. You can call me almost 24 hours a day. I may actually be up and answering this at whatever time you call, and we would be very happy to hear from you. With that, I will say good evening